Alright guys, good morning. So welcome back to Machine Organization. Yesterday we began Lecture 9 talking about low-level C programming. In particular, we looked at number representations. So if you haven't watched that, that's going to be important for today. This is essentially part 2 of that lecture. So quick review, we talked about 3 different number representations. Signed magnitude, which was used in very old computers. The ones complement method, which was used in also very old computers. And both of those suffered the same disadvantage in that there's more than one way to represent 0. And then finally we wrapped up with the two's complement method of representing numbers. And we kind of went through some stuff about the minimum and maximum integer that could be represented using these representations. And also how to translate between decimal numbers and the binary representations of each of these types of number systems. Alright, so today I'm going to jump right over into CSL machine and just demo how to use this new information in C. So C is a two's complement representation. I'm going to show you how we can verify that. And then I'm going to talk about how to enter a specific bit pattern. Printf deals with these a little bit weird, very directly I suppose might be a better way to say it. So I'm going to demo that and show you how to take advantage of that. We'll also wrap up then with sizeof and min-max for this first piece of today's lecture. So, alright, I'm going to pause here, jump over on a CSL machine, and bring up some code. Alright, so I've just jumped over onto a CSL machine. I've got Vim open with my file. I want to point out I've got just a bare bones framework here. I'm going to be filling this in. I'll do one line, pause the video, I'll do the rest of the lines, and then you guys can follow along. And this code will be available for download on the code section of the Canvas page. So first up, I've got standard IO so I can print stuff out. And then all of these min-max values for the different primitive types are found in limits.h, so I'm including that. And now first up, to just enter a specific bit pattern, all I need to do is put this in as hexadecimal. So I'm just going to 1, 2, 3, 4, 5, 6, 7, 8. No spaces though. So the size of an integer is 4 bytes, so I need 8 hexadecimal characters. So just as an example, I'm going to enter the entire all ones representation. So 32 bits, all of them 1. So that's FFFF. Okay, and then let's print this out. So let's see here, printf. And there's 2 different ways I want to show you how to do this. The way we've been doing this whole time, num as decimal. Let's go with signed decimal equals, and then we need a %d, no. So we just do this, and then we go ahead and compile this, GCC. I'm going to call this limits, and then my original file name was limits.c, m32, and all the warnings, and then limits. And when I run this, oh, I forgot the new line, it's going to print out the signed decimal version, so this is going to be signed. And when I put in the entire ones bit pattern, I get a -1. If you remember that the entire ones bit pattern -1 does represent the two's complement. Actually, let me pull that slide back up from yesterday. Yep, here we go. Just as a quick review, we can see the two's complement method is the one that only has one value for 0, and indeed the entire ones bit pattern is -1. And to get that, we can just take the negative sign in front of this 2 raised to the n first digit, and everything else becomes positive. Alright, I just jumped back over here. I put the new line in, so this is actually going to look good in a second. I'm going to copy this line, paste it again, and then hold on, grab this line, paste it again, and then I'm going to insert there we go, unsigned. So we'll do an unsigned version of this also. And then the keyword here is u. This will print the number out as an unsigned decimal. So I just want to talk a little bit about how printf is doing things. Printf takes the bit pattern. It doesn't care what it is. And this, whether it's a D or U, is telling us how we want it printed out. In fact, one more as long as I'm right here. I'll make another copy and print this out as a hexadecimal number. We'll get these all to line up good. Oops. I think I forgot the Where is it? Yes, I did. I forgot to change this to the X. So replace that with an X. Capital X will give us the capitalized version of the letters, and lowercase x will give us the lowercase numbers. So then I just need to compile this again. There we go. Totally worked. And limits. Alright, so here we go. As a signed decimal, this is going to be number -1. So this is using a 2's complement representation. As an unsigned decimal, the maximum number we have is just using the signed magnitude version without, well, just the magnitude version, no sign. All the bits are used, so we can see that the all ones representation is going to be the maximum value we can stick into an integer. And then we print it out as hexadecimal. It doesn't give us the 0x, but it gives us the bit pattern that we put in. Alright. Next, I just want to go back and talk about the size of all the different primitive types, and just show you guys how to get all of them, put them all in one big table. I know I mentioned this when we were talking about primitives early in the semester, but I don't think I included absolutely everything. So let me go ahead and real quick add one of these, printf. So this is going to be size of, and then whatever I want to do here. I'm going to do size of char first equals, and then I need the percent. Here we'll do this as a decimal, and then size of char. Let's throw a new line on there. So let me just do this one, and we can see that the size of char is 1 byte. Alright, I'm going to go put the rest of them in, and I'll be right back and demo this for you. Alright guys, I just put the rest of these back in. Okay, so the different primitive types that we have in C are going to be the char, short, int, long, and I don't think I mentioned long last time. But anyway, yeah, there's an even longer version of the int. The only guarantees that we have, char is going to be 1 byte on the current version of C. Short is guaranteed to be bigger than char and less than int. Int is typically 4 bytes, short is typically 2. I'll see that in a second. Long is guaranteed to be greater than int, and long guaranteed to be greater than long. Greater than or equal to on all of these guys. And then we have unsigned versions of all of these also in C. So let me go ahead and, just one more thing I need to mention. This is also short int, but we can abbreviate that to just short. This is long int and long int. All three of those options will work if we put on the int, just like that. It's not required though, and I'm going to abbreviate. So let me just get out of here. We'll save that. Let me see here. Got to compile this, and then we've got to run it. Here's what we're getting. So I've retained that stuff at the top, and then I'm just building up on this. So the size of character on this machine with this compiler is 1 byte. Short is 2 bytes. Int is 4. We saw this before. The long actually has the exact same number of bytes. So this just verifies for me right there, 4 bytes, that this indeed was the entire one's bit pattern. I needed 4 bytes worth. It's 2 hexadecimal characters per byte. So just wanted to show you that that was, I'm doing it right, I'm not messing up. And then the long is the one that's actually bigger than an int at 8 bytes. We also have unsigned versions of all of these, and they come out to exactly the same, 12448, 12448. Alright, so next up I want to take a look at the maximum and minimum values. We can get these out of C also. It's pretty simple. Focuses on the wrong screen. Printf. So we're just going to do, let's see, what's it called? Char max. We'll do char min in a second. So char max is equal to, and then print this out as a decimal. And then, whoops, not bytes. I'm just looking at the previous line. And then we need, char max is that first one. Alright, I think I got that right. So look good, you guys. And then the min is just, I'm just going to change this to, whoops. That was not in the right mode. Insert, char min, max. And by typecasting these to the decimal, printf is going to just assume that I have an integer here, and it's going to change the char, which only gets 1 byte, to a to an integer, so that should this be quite large, basically this will verify for us whether it's, actually it verifies whether it's signed or unsigned. Check this out. Okay, so the maximum value for char is 127. That's the maximum value you can put in a signed 1 byte number. It's going to be 0, 1, 1, 1, 1, 1, 1 as the bit pattern. 7 ones, I think. And then the minimum value is going to be minus 128. So that's going to be the 1, 0, 0, 0, 0, 0, 0 with 7 zeros bit pattern. All right. So those are the maximum and minimum values for a char, and it verifies for us that char is actually represented as a signed number. So all those ASCII values we've been putting in, so far we've only used ASCII representations for letters that are less than or equal to 127. All right, so here's the idea. All of those terms are built into C, just hash-defined constants for the maximum values and minimum values for things. I'm going to go put in the rest of the chart so we can see all the different primitive data types. Bear back. All right, guys, I got the rest of these put in. I wanted to do this for a couple of reasons. First, so that you have the command here to bring up the maximum and minimum value for all the different data types. Second, I just want to go through and make sure that you're aware of everything that's available. And then to talk about the weird formatting things that are required to make all of these print correctly. So just up at the top, I've got my char min, and I'm printing this out as a decimal. So this will take 1 byte value and turn it into a 4 byte value. And we'll talk about that in just a second. But then it's going to print out the minimum value for the character. This will do the maximum value. Then there's two other versions here. I've got a signed character with a minimum value and a maximum value. And those are still just going to be printed as decimal values. And then the unsigned version just has the prefix U on this. I've got this commented out. I just want to mention that there is no unsigned character minimum value. It's just going to be 0. In fact, see, it's not yellow in this screen. So I'm going to leave that here so you guys can see that it is in fact not available. But it's always going to be 0 for the unsigned versions of all these things. And then in the next block here, I've got these short variables. Abbreviation for that is shrt min and max. And then the unsigned version is u shrt. I'm still going to be printing these out as decimals. So we just saw up above that each of these are 2 bytes. So it's going to turn them into the 4 byte representation and then print them out using the %d. Okay, and then, and this is going to be printing them out as signed or unsigned. So even an unsigned 2 byte variable will fit into 4 bytes printed out as a signed version. That's no problem. Okay, and then the integer version, I did need to make one change. Because this %d prints them out as a signed variable, it's just going to take that bit pattern, assume it's represented as a 2's complement signed bit number. So for the unsigned version, that's going to exceed the value that we're allowed to put in a signed version. It's going to be about double. So in order to do that, I need to tell printf to print this out as an unsigned integer. And then for the long variables, so long min, long max, I need to add the ld. So this will tell the C compiler that I need to use printf version for the long variable for long integers. And again, the long unsigned, because the long unsigned version will not fit in the signed version. It'll be too big. In fact, if you guys want to experiment with that, push that back to a D, and you'll see what I mean. You're not going to get the same value. Okay, and then for the long version, this is the 8 byte version. I need the LLD. So this is going to print out, this is for the printf statement. This is just telling it to format as an LLD variable, long decimal or long unsigned. All right, so let's go take a look at these numbers real quick. So just quit, compile, and run this. All right, so here we go. So we can see here, this is the one I had up before. The character minimum is negative 128. But the max is 127. So we're getting that range where there's just one fewer number in the positive side. And that's sort of because when it divides it in half, it includes 0 with the positive numbers. Okay, and then C has a signed character and an unsigned character. So again, we can see that just the straight up char variable is signed, and it matches the signed char variable, but I can declare it to be specifically signed if I want to. For the unsigned version, we see we get all of the bits being used to represent the largest possible magnitude. So all ones is going to be this max number. They're all used for magnitude. I think I misspoke a second ago. Okay, and then for short, we get 2 bytes, so we see these numbers are substantially larger than those. And again, the regular version is unsigned. The regular version is signed, so I've got a sign here, and then unsigned. The integers, again, more of the same. The long has the exact same numbers as for the integer, just because they're both represented as 4 bytes. And we can see also here that this one ends in a 7, the negative one ends in an 8, so we get one extra number that we can represent that's negative, and the 0 gets included with the positive side of things. And then if we have some truly enormous numbers, the long representation is available to us should you need it. Great for things like the Fibonacci sequence or factorial, or things that blow up. Should you go, when you get to the very far out there, lots of iterations of those algorithms. Okay, I'll be right back with the next topic. Oh, before I do that, I just want to talk about one more quick thing with formatting. So it's irking me a little bit that I've got a negative sign and the right hand column of these numbers isn't lining up. So I'm going to go back and add one little detail to fix that. Okay, so here's all of my print statements. Now, when I'm printing out the maximum value, I can just add a plus sign right here for all of the maximum values, and then it'll add a plus sign, and then they'll all line up really well. So let's see, we'll just do that one, that one. All right, whoops, I missed. See what this looks like. Oh, check it out. There we go. Okay, now they're all lining up. I love it. 8, 7, 5, all in the same column. Looks like I missed 2 of them. I'll go ahead and did I miss them? Or does it just not do that? Nope, I put them in. The positive symbol must not be available for these guys. All right, anyway, yeah, right back with the next topic. All right, I just noticed when I was working on this next piece that the compiler actually gave me a warning about the plus flag being used with the unsigned version of printing. All of the numbers have to be positive for unsigned, so that makes sense that it's not available. Okay, I went back and I made some changes for the next topic. I got some material added. So I just went back. I'm here. I want to just talk a little bit about what printf is doing. It's taking the bit pattern exactly. So if I look here, I've got int n. I put in the all ones bit pattern. Then I'm just going to print it out. This is the decimal and the unsigned version. This is the exact same thing I did at the top. But then what I'm doing is I'm casting this to an unsigned variable. I'm basically taking a new variable unsigned. I'm setting it equal to the same bit pattern, and going through and I'm printing it out as a decimal and an unsigned version again. So yep, and as decimal and as unsigned. The unsigned version as a variable, as a decimal, and unsigned. So let me just go real quick, make sure I compiled this. Yep, looks good. And then we'll run this. There it is. And we can see we get the exact same thing. I'm looking down here at the bottom in the highlighted piece. So n is equal to -1 here. And then I've got the maximum value for an unsigned integer right here. So what printf is doing, it just takes that bit pattern. Oh, and here's that maximum value for an unsigned. These do indeed match. So it's just taking the bit pattern and saying, okay, represent it as a decimal. All ones is going to be -1. Represent this as an unsigned variable. So all the ones is the maximum value. Even though when I turn it into an unsigned, printf is just going to take that same bit pattern and say, okay, well, we want it to be decimal now. Switch it. It's not going to do any checking to see if my variable type is actually unsigned. It's just going to say, you're the programmer, you know what you're doing, you're an expert, I'll do it. So it's printing it out as the -1, even though unsigned should never have a negative number. And again, when I print it out as an unsigned variable, then I do get that max value. So it's up to you to make sure that how you're printing things actually matches what's going on with your variable types. All right, so the next thing I want to talk about is what happens when we want to change from one number type to another. So example, typecasting. For example, if I have like 1 byte as a character and I want to store that data in a short with 2 bytes, or a short stored to an int to long. So these are the ones that are really no problem. I'm not going to lose any data. So for example, the char only has 1 byte. I'm going to a larger data type. This only has 2. I'm going to a larger data type. Int to long, they have the same number of bytes. I would not expect this to be any problem at all. I just used the same bit pattern. And then long to long, also, we're getting more data. We're not going to lose anything. All right, so let's take a look at an example of just going from a char data type to a short. Okay, first of all, let's take a look at positive numbers. And these could either be signed or unsigned. They have the same bit pattern in C. And for my example, I'm going to do decimal number 26. So as a review, guys, pause the video, figure out what this is in hexadecimal, and I'll reveal the answer in 3, 2, 1. Done. There we go. Okay, so in hexadecimal, this is going to be 1A. You can think about it as the A is going to represent 10, and the 1 here in the 16th place is going to be 16. So 16 plus 10 is 26. All right, now next up, we're going to need this in, all right. Oh, and as a short, I get an extra byte. So that's going to be an extra 2 zeros and then 1A. So this is the 1 byte version and 2 byte version for char and short. So next up, because we're talking about bits and low-level C programming, we're going to need these numbers represented in binary to talk about what this machine is doing on the inside when it takes this bit pattern and turns it into this one. So go ahead, take a sec. I'm going to reveal the binary version of these in, pause the video, do it yourself, double check. All right, here's the answer in 3, 2, 1, go. All right, so here we are. So 1 is just going to be 0001, those first 4 bits. I'm going to put a space in to break these into the hexadecimal size pieces. And then A is 10, so that's 8 plus 2 makes 10. All right, and then this version, 0 here is just 0, 0, 0, 0, 0, 0, 0, 0. And then this should be the same, 0, 0, 0, 1, 1, 0, 1, 0. Okay, now when we do this, it's actually pretty easy. All we need to do is fill this, the rest of the bits in with 0 so that we have the same number when it's positive. All right, now let's take a look at an example where we're using negative numbers. All right, so again, I'm just going to do negative 26. Go ahead again, get some practice here. We need the 2's complement binary version of decimal number 26. So I'm going to go ahead, pause the video, figure out what you think this is, commit, write it down, and I'll reveal the answer in 3, 2, 1. Here we go. Okay, and just as a quick review, if I can just sort of take this, what I'm going to do to go quickly from a binary positive to a binary negative version of that is just take the 1's complement to start with. Step 1, 1's complement. So this 0 here, where's my mouse? All right, I want to point. Pointer options. Where is the arrow? Visible at all times. Okay, so this leftmost one, the sign bit, is going to be 0 here. I need to flip it to a 1. That 1 turns into a 1. So 0 to 1, 1 to 0, 1 to 0, 0 to 1, 1 to... Okay, this would be a 0, and then 0 to 1. Actually, let me make a different slide. Hold on one sec. All right, I just went back and added a little bit. So I'm computing the negative 26 in 2's complement binary. Positive 26, I just copied that number from above, 0001, 1010. And then to take the 1's complement, all I do is flip all the bits. So hopefully I got that right. You guys can check me out. The previous slide had the final answer where I'd already done both of these steps, and I just wanted to break it down a little bit. So final step is to add 1 to this number. So that's going to take this digit here at the far right. It's going to go from 1 to 2, but 2 in binary is not allowed, so I need to, what's the word, carry. So I'm going to take this, the pointer went away. All right, pointer options, arrow, visible. Okay, so this is going to be a 2 after I add 1. That's just going to carry over, and I'm going to have 1, 0 at the end of that. Okay, so same deal for the short version where I get 2 bytes. So I'm going to go ahead and flip all of these digits, all the zeros turn to 1, and then this is going to be 0, 0, and then again I'm going to do the exact same thing. I'm just going to add, so complement this, so it becomes a 1, and then I add 1 to it, and I've got a carry, end up with 1, 0. So this should be the last 8 bits should identically match, and all I needed to do here was fill this all in with 1s. Alright, so next thing, just to get a little bit of practice, why don't you guys take a second and try and turn these two numbers into hexadecimal. Answer in 3, 2, 1. There we go. Okay, so 1111 would be F. That's always the biggest one. I've got 1 less than this, so E comes before F. And then this is going to be no 8s, 1, 4, 1, 2. So 4 plus 2 is 6. So E6. And again, 1111 is always F. So in as a short, this number will be FFE6. Alright, so the idea here, what's going on inside the hardware, is an idea called sign extension. And so if I look at the sign bit here, this is going to be the 1. If this bit is a 1, it'll be a negative number. If it's a 0, it'll be a positive number. So 0 and 1. So this not only contributes to the number, but tells us what the sign is. And so all we need to do is take whatever this number is to go from a 1 byte to 2 byte or whatever, as long as I'm increasing. And I just need to fill in all the remaining new bits with whatever the sign is. So this will always be 0 if it's positive. These will always be 1 if it's negative. A good way to remember this is to just think about positive 1 and negative 1, because those numbers are very easy to remember in binary. So it's just 0, 0, 0, 0, 0, 0, 0, 1 for the 1 byte version, and then this the positive 1 in 2 bytes is just going to add 8 more zeros. So I've just extended that 0. And in decimal, it's just negative 1 is always just all 1s and all 1s. So to get there, all we need to do was take this sign bit and extend it out. So hopefully that's useful. And again, I've got the hexadecimal here for you guys, 0, 1 and 0, 0, 0, 1, FF, FF, FF. So just the all 1s bit pattern for the negative ones. All right, let me jump over into some code for a second and we'll do some examples. All right, guys, I jumped back over into C and just put together some code briefly in a file called typecasting. And here's what I've got going on. Start here with char C. I'm entering a value in essentially in binary, or the hex version right here. This is the example I just did in PowerPoint, so this should be 26, and we'll verify that in a second when I print it out. And then I'm taking the same bit pattern and storing that value in a short. In fact, I can do one more little thing right here. I can actually cast directly C into a short. And then when I go ahead and print this out, I'm printing the decimal version, should be 26. I'm printing the hex version. Printf doesn't actually show me the leading zeros, so it won't be obvious that we've changed size. And there is no char that I can put together that will not be, well, positive, that won't have the leading zeros here. So let me just write and save this. And then when we run this, we can see that, yeah, decimal C is 26, hex value is 1A, and it's successfully cast. There was no, well, let me actually, I skipped all the messages and stuff. Let me just compile this, no warnings, and then we'll go ahead and run it again. And yep, we can see that we get the same number. So this is not all that useful because printf won't print the leading zeros. Let's go ahead and do a negative number real quick, and then we'll switch into the ones where we start losing data, the good ones, where we're going from 2 bytes to 1 byte. Alright, so this is actually really easy. Let's see, I've got 1, 2, 3, 6 lines, so copy 6 lines. We'll paste those guys right here. I've already declared C, but I want this to be negative 26 now. So instead of a hex value, I'm just going to put in minus 26, and we'll print that out as decimal and hex. So we'll see what it is, and we can verify what we had before. And then I already have a short declared, so S. We'll still keep that. We'll cast C into a short and see how this works. And then I'm just going to be printing out these same values again. So write and quit, we'll compile and run. Here's what we get. Okay, so interesting. I'd forgotten this happens. Okay, hold on one second. I'm not printing these as char and short. I'm printing them as hex decimal values. So let me just walk through what we've got, and then I'll go fix that so we can actually see the right number of bytes. So here's the positive versions. In negative, we've got negative 26. When we cast that to hexadecimal, or write that in hexadecimal. We got E6. That's exactly what we had before. And then when we stored that in short, we got just these last 4 digits, FFEE. So what I did here is I used the actually, hold on. I'm gonna go look that up and see if there's actually a version that prints hex as with 2 bytes and 4 bytes. One sec. All right, sorry guys, I couldn't find it. Let's make this a much less interesting example than I was hoping for. So yeah, the printf function takes all of the values. It's just a binary bit pattern. It turns it into an integer for us with 4 bytes, and then that's what it's printing out. So we can in fact see that when turned into an integer, the character is going to be prepended by these 6 sign bits. So basically 24 ones are prepended to this value. All right, so now I'm going to switch over and do a little bit about what happens if we take a larger int and cast it into a much smaller, shorter char. So let me go back to PowerPoint and do some examples there and explain what's going on. Okay guys, I'm back. I found a way to demonstrate what I was trying to do with long values. So there is a command that lets me print, so I'm looking at this piece right here. All right, there is a command that lets me print hex values, so that's the x of long values. So that's going to give me all 16 hexadecimal bits or digits, should I need them. There's probably a way to do it for char and short. I just couldn't figure it out. If it's in the book, somebody give me the page number because I overlooked it, and if you guys find it, post a link on Piazza for me. That'd be awesome. Okay, here's the idea. I'm putting in a long value, so that's 8 bytes. So that's 16 different hexadecimal characters. So I just went with 1 through F. We can see that, and then this will print out, and I'll show that it works. Excuse me. And then for the demo, I'm using the positive value, an integer this time, 1, 2, 3, 4, 5, 6, 7, 8. So I get 8 bits, 8 bytes. No, 4 bytes for an integer. That's 8 hexadecimal characters. Okay, and then I'm casting this to a long value, and I'm just using that same variable, so I could copy and paste the printf command. Here we go. We're doing the same thing. We're printing out I as a decimal, and then the hex value for I. Now it's still going to chop off all of the zeros, so we're not going to be able to see the same thing. All right. Yeah, let me just run this, and yeah, I quit. Compile and run. Okay, so check this out right here. This line demonstrates that I do get to print all the values of those digits, and then this line here is the integer version. So that 1, 2, 3, 4, 5, 6, 7, 8 in hex is this number, and it does truncate all those leading zeros and prints it out. So there was no error. This totally worked. I'm getting the same number in hex, even though it's not showing me all those leading zeros. Okay, let me do a negative number real quick. Alright guys, I just thought this made an interesting example. Negative number, I'm using the integer minimum, int min. We just saw that earlier in the video. So it's definitely going to be a negative number for signed integer. And then I'm casting this to a long. So, and again, we're going to see that this totally works. It'll print out the number for me. We can see what that is in hex, the least possible integer, and then we'll print it out in as the long version also. All right, let me just go back and run this. There we go. Where was that? Compile and run the code. So now we're looking at this bottom block here of the new stuff. We can see that whatever the minimum value is, negative 2 billion. In hex, that's just going to be 8, followed by a bunch of zeros. And 8 is 1000. So this is the minimum possible value. Basically, we take the all zeros and just put a 1 in that leading sign bit spot, the most significant bit. And that's what we get. And then when we cast this to a long, we still get the same number here. We still get the same number here, but it's now been prepended with 8 more Fs, and again the second half is identical. Alright, so next up I'm going to go back, now for real, I'm going to go back to PowerPoint. I'm talking about what happens when we go from a larger bit number to a smaller bit representation. Alright guys, let's talk about typecasting from things that are much too big to things that don't have enough room for them. So for example, a short that's 2 bytes being cast into a char that's only 1 byte. So first, I'm going to do an example that if it fits, so things that are any number that's less than char max or less than 127, it isn't really going to be a problem either. So as an example for a positive number, signed or unsigned, they're the same representation. So if we take decimal 26 is 001A as a short, and here's the binary representation of that short, the binary representation of the char, and all we need to do is chop off the leading zeros, and we can represent this. Exact same thing with the negative numbers. For negative 26, I've got the binary representation and for the char over here. All we need to do is remove these leading 8 ones and just keep the rest of it, and we're good. So typecasting basically works by chopping off the leading bits and just retaining the least significant bits that fill up whatever the data type is. It works the same for all of those. All right, next let's take a look at the interesting problem. What if we're trying to cast a variable, a number that's too big? So short holds 2 bytes. I could put in some number that's greater than 127 and cast that to a char. And let's just see what happens. And I'm going to do this more as an experiment. So I'm going to just choose a positive number. And I know that I need more hex digits than 2 because char will only hold 2. So I'm just going to choose 1, 2, 3, 4 in hex. I know it's too big. I have no idea what the decimal is. I'm going to use C to figure that out. And then I do know the binary representation. So 1 is just 0001, 2 is 0011. But I'm curious what happens when I perform this operation. So I'm going to jump over into C and demo this. So here we are back in Vim, and I'm looking at this section of the code right here. Positive number short going to a char. And if I have a number that fits, so 1, 2 only takes up 1 byte, and I cast that to a char, so typecasting, I just need the type in parentheses followed by the whatever I'm casting. And then I'm going to print this out. First the short, and then the char version. Okay, so let me just save that. We'll do the compile. There it is. And then we'll run the code. Now we can see that hex 12 is 18. Yeah, that makes sense. So 1 would be the 16 plus 2. And there's no difference between the char and the hex version, or char and short. It works just fine. All it did was chop off those leading bits. All right, let me jump back over to this, and let's choose, let's do a negative number. How about something like negative 7. Run that. Okay, here we can see that -7 in hex is a whole lot of f's followed by 9. And remember, we have to do that 2's complement conversion. I think I'll take the 1's complement and then add 1 as the easy way. So you guys can go back and look at the slides and verify for yourself that that's true. And when we print things out in hex using printf as just the %x, it gives us all of the digits as though it were an int. So a 4-byte version. And again, we get the exact same values for char and s. So things that fit seem to work just fine. Now let's pick something that doesn't fit. And the example I wanted to do from PowerPoint was 0x1234. I know this definitely will not fit. So when we cast this to a char, let's see what happens. So let's see here. Write and save, compile, and run. Okay, now when we look at this, so here's the answer. I let C do the conversion for me. Hex 1234 is 4,660. You guys can verify that on your own. But what happened now is the decimal version when I cast to a char is only 52. It is significantly changed. It almost looks like a random weird change. We need a number between, well, negative 128 and positive 127 when we do this conversion. So what it looks like it's doing is it's only retaining the least significant bits. So 1, 2, 3, 4 got changed into 3, 4, and those most significant bits got chopped off. So this system works well for numbers that already fit, and it produces indeterminate results for the most part for numbers that do not fit. All right, I'm gonna go back. Let's try a negative number, just as an experiment. So let's see here. Go back here. What are you guys thinking? So a negative number that doesn't fit. How about, so anything smaller than minus 128. So let's go with minus 200. That should be small enough. We'll write that, compile it, and run it. Yeah, negative 200, a whole bunch of F's and 3 8. Okay, yeah, that kind of makes sense. You guys can check that on your own. But then when we cast this to a decimal, notice we're actually getting a positive number for the char value, 56. It's almost random. So when we have numbers that don't fit, you guys can almost consider this to be an indeterminate result. There is math that will do this. It's only retaining the last 2 hex digits or the last 8 bits. Excuse me. Yeah, only retaining the last 8 bits. So that's how that's work. It's just going to truncate the number to whatever size really fits, and it's losing the most significant bits. All right, one last thing, and I think this is the last typecasting thing I want to talk about. I just need to point out too that sign extension doesn't actually happen for unsigned types. That is signed types only. And just as an example of this, if I take a char, so this is the number 1, and cast this into a short, I just need to prepend a bunch of zeros because this is the binary representation for 1 when I have more bits, if I don't have a sign. Now, if I'm using, this is going to be the maximum possible value I can hold in a char, that's 127. It does start with a 1, and if this were a signed type, this would be the sign bit, but as an unsigned version, I'm going to just add zeros again so that I still get the 127 as a signed short. Oh, and I should have updated this. I'll do it before I post the slides, but this should be signed char and signed short, just like in the code, which we can see right here. So I'm creating new variables, unsigned. Whoops, I forgot the char. Let me fix this. Time out. All right, I got those fixed, I think. So now I've got an unsigned char, assigns the value 1. I'm casting this to an unsigned short. There's my char. Right there's that. And then I'm just going to print these out, the short and the char. And then the second example, I'm choosing a number that begins with a 1. So in this case, I'm using all 1s. So 8 ones in a row in binary. And then casting this to an unsigned short also, and then just printing those out. All right, so let's get out of here. We'll compile this, and then we'll run it. And here we go. Down at the bottom, we can see that the unsigned short version, when it's a 1, it doesn't change. 1 doesn't change. They're both the same in hex and binary and decimal. And then when I choose the one that's all F's, 255. Have I been saying this wrong the whole video? 255 is the max char. 255. I'm pretty sure that's not the number I said last time. I hope you guys were screaming at me. Apologize for that. Anyway, so FF there. And when we do the casting to a larger size, it doesn't fill in with 1s, even though this is begins with a leading 1. It's all 1s. Instead, we only get 8 zeros and then 8 1s. So it doesn't do sign extension for unsigned types. It just fills in with zeros. All right, that's going to do it for this part of the video. This will be section 2 of this part on bits and low-level programming. So I'm going to go edit this, get it put up so you guys can start working on it immediately. And I'll be back with the next section. It'll probably take me a little bit to put together, but hopefully pretty soon. All right, anyway, have a great day.